So now that we've seen how to graph linear equations using tables of values, we're going to look at a more efficient technique using what we call the slope-intercept form of a line. So it's just a special format, a special way for us to write the equation of a line where y is isolated on one side of the equation and where on the other side you see a term with x as well as a constant term that doesn't have an x attached to it. Now the number that's the coefficient in front of x, that's going to be our slope, which is the steepness of the line. And then the constant, which has no x attached to it, that number will represent the y-intercept, which is the height at which our line crosses through the y-axis. The slope can be thought of as rise over run. That's the steepness of the line, and you've probably heard of rise over run before, but it's the vertical change, how much do we go up or down, compared to the horizontal change, how much do we run left or right. The y-intercept is a point of intersection, the point where it intersects or touches the y-axis, so we can think of it as an ordered pair, where x is 0 because we're not going left or right, we're centered on that y-axis, going up or down, whatever the number is for our constant. So here's an example of a linear equation written in that slope-intercept form. Y is already isolated by itself, and you can see the coefficient on the x here is 4, and the constant term is -3. And so just at a glance, I can look at this and see that the slope of this line will be 4, the coefficient in front of x, and I can see that the y-intercept is this -3, but because the y-intercept is actually a point, I am going to describe it as an ordered pair where x is 0, because we aren't going left or right, we're on the y-axis, but where the y value is the constant, in this case the -3. So I have a point and I have a slope or a steepness. And what I can do is I can use those two pieces of information to get my graph right away. I'm not going to have to do a bunch of plugging and chugging to fill in a giant table of values. I can use just those two pieces of information. So first I'm going to begin with the y-intercept. That's the one point that I have been given. Again, it comes from the constant term here. I'm going to take that point. 0 is my x value, so I don't go left or right. I stay centered, but I do go down 3. So my y-intercept is right there. And then from that point, I'm going to use my steepness of my slope to gauge how my line cuts through that point. So it's going to be helpful for us to think of the slope not just as whatever that number is in front of x, but see if we can't think of it as a fraction rise over run. And I know we're timid when we think about fractions, but this will actually be very helpful for us. Let's think of 4 in a couple different fraction forms. So if you were to take a whole number like 4 and turn it into a fraction, you'd simply just put it over 1. So you'd say 4 over 1. But I'm going to take it a step further and have us look at it two different fraction ways. I'm going to look at it as +4 over +1. That's one way to view the number 4 over 1. I also can view it as -4 over -1. It sounds weird that we would even think about these two different options, and I'll show you why we would do that in our picture in just a moment. But you can confirm 4 over 1 is 4, -4 over -1 is also 4. So they both give me that slope of 4, but looking at those two different ways and thinking of it as the rise over the run, if I'm rising +4, I'm going up, where if I'm rising -4, I'm going down. The run is that horizontal. If I'm running +1, horizontally that positive number would be going to the right. If I'm running negative, I'm going to the left. So what this is going to do is it's going to give me several different possible directions I can rise and run. I can go up 4, right 1 from this initial point, or I could go down 4 and left 1 from this initial point. So let's see what that does for us. From this initial point, from this y-intercept, let's try going up 4, right 1. So up 1, 2, 3, 4, and to the right 1 would put us right there. And technically just those 2 points, that's plenty for us to be able to take a straight edge and connect those two dots. But what we'll plan on doing, just like we did in the previous videos, we will try to get additional points to add in some extra accuracy. So what I would encourage you is, however big your graph paper is showing your grid, I would extend your points basically to fill that space. Because if we can fill that space with points, we're filling that space with accuracy. So from that initial point, I went up 4, right 1. I'm going to keep doing that same pattern. So from this next point, let's go up 1, 2, 3, 4, and right 1. And now I have a third point that is still on the same line. And from there, it looks like I've got enough space to keep going. From that point, let's continue to go up 4, 1, 2, 3, 4, and to the right 1. And at that point, I think I'm out of space going in that direction. But rather than just going up 4, right 1, up 4, right 1, up 4, right 1, there's a different way I could have gone to fill in some of this space down here. And that's this other option, which was down 4, left 1. So if I go down 1, 2, 3, 4, and left 1, we're getting a point that's still on the same line. So I can go up 4, right 1, or down 4, left 1, as many times as I need to get my space filled in. Once I've got points filling that space, I can go ahead and take my straight edge. I can connect these dots with a straight line, and as we did before, remember that our lines must have arrows on both ends to show that the line does extend forever in both directions. But this is a much faster technique for us once we get used to it. It's very efficient compared to the tables of values. It does only work for lines, so that's the one disadvantage, is that it doesn't work for other kinds of shapes. Of different kinds of equations, but for lines, it's very efficient, it's very quick. So we're going to be writing slope-intercept form where y is by itself. We'll identify the slope as the coefficient on x. We'll identify the y-intercept as the constant term. Again, writing our y-intercept as a point and trying to find our slope in 2 different fraction forms to help us fill the space in 2 different directions from the center line. So let's try another example. Okay, so here we have another example of a linear equation which is already written in slope-intercept form with that isolated y, where I can see a term with x and a constant term. I'm going to go ahead and just by looking at that form, I'm going to identify the slope, which is going to be my coefficient in front of x. And then I'm going to also identify at a glance my y-intercept, which is found where my constant term is, but remember that your y-intercept is a point, 0, comma, whatever that y-intercept or whatever that constant term is. So I have a slope and I have a y-intercept, and to graph, I begin with that y-intercept where I go not horizontally left or right, I stay center, but I go up 1. So there's my y-intercept at positive 1, and from there I'm going to use the slope to go up or down or left or right to kind of figure out where the line goes as it cuts through that point. So again, to help us, let's take a look at a couple different ways to view this slope of 3. So if I want to think of it as rise over run, think of it as a fraction. You can think of 3 over 1. But let's go with 2 different versions. Let's go with a positive 3 over a positive 1. That's one way of seeing the number 3. Let's also look at negative 3 over negative 1. So again, I'm writing the 3 as a fraction 2 different ways. Positive 3 divided by positive 1 is 3, but also negative 3 divided by negative 1 is also 3. And so this gives me 2 different ways to move. Since this is rise over run, vertical over horizontal, I can go up positive 3. I could go right, positive 1. Here for, again, vertical on top, horizontal on bottom, I can go down for that negative 3, and I could go left for that negative 1. So let's see how those directions help us move from this initial point. So I start at the y-intercept, and from there, I try these different ways to count to get additional points. So let's try first the up 3, right 1. So from my initial point, I can go up 1, 2, 3, and right 1. And there's another point, and that's technically all I need to get my line, but again, more points means more accuracy. So let's keep that pattern going. So we went up 3, right 1 to get our second point. Let's do that again. Up 1, 2, 3, right 1. There's another point, and then from there, if I've got the space, let's go again. 1, 2, 3, up, and right 1. They're all looking like they're in line. This is a good thing. Now, I've run out of space going in that direction, so now let's try a different direction. The down 3, left 1 will help me go the other direction. So instead of up 3, right 1, let's now go down 1, 2, 3, and left 1. And I'm seeing that I'm still on that same line. And then from there, again, I just want to fill in the space so that I get full accuracy in this big picture. So I'll keep going down 1, 2, 3, and left 1. And I think I can fit one more. 1, 2, 3 down, and left 1. So I'm out of space. Let's go ahead and take those points, connect them with a straight line. Again, the more points we have, the more accuracy we gain. And again, don't forget your arrows to show that this line continues with the same up 3, right 1, or down 3, left 1. It keeps that same pattern forever. That's what those arrows are telling us. So here we have another example of a linear equation written in slope-intercept form. By looking at this form, I see that the y is isolated. I've got an x term and a constant on the other side, and just looking at it, I can identify that the slope is -2. It's that coefficient on x. And I can also see that the y-intercept, which is our point where the line will cross the y-axis, that y-intercept will happen at 5. So I will write it as a point 0, 5. So again, that y-intercept is always a point 0, whatever the constant number is. So as I go to graph this line, I'll start with the y-intercept. So I don't move left or right, but I go up 5 for my y-intercept. From there, I'll use the slope to help me figure out where I go from there. Now again, we want to think of the slope as rise over run. We want to think of it as a fraction. And we'll think of it as two different kinds of fractions. Let's start by just taking that -2 and putting it over 1. If I put a whole number over 1, now it looks like a fraction. So I can think of it as -2 over +1, but I can also think of this as +2 over -1. We've seen before that it doesn't matter where the negative is. It could be in a neutral position, it could be up high, it could be down low, but -2 divided by 1 is still -2. 2 divided by -1 is also -2. So it's just two different ways to say -2 as a fraction. And based on those two different ways, it gives me different directions to go. So if I have a negative rise, I'm going down 2. If I have a positive run, I'm going to go to the right 1. And then over here, if I have a positive rise, I'm going up 2. If I have a negative run, I am going to the left 1. So I have a couple different options here. Let's just do one at a time. So we begin with that y-intercept we found, and let's try this first option, down 2, right 1. So from 5, from that initial y-intercept, let's go down 2 and to the right 1. And I can go with a line just between those 2 points, but again, I want more accuracy, so I'm going to keep that same pattern from this new point. Let's again go down 2 and right 1. They're still lining up, which is good. Again, from there, as long as I've got room to move, let's go down 2, right 1. And again, down 2, right 1. And I'm going to be a little off here, I think. Let's see, down 2, right 1, down 2, right 1, and I would just keep doing this until you run out of space. So down 2, right 1. So I'm out of space down there. Now that's filling up all this area to the right of our initial point, but we want some information over here as well, again, just for that accuracy. So from that first point we gave, that y-intercept, let's now use the other option, which was up 2, left 1. So from the 5, let's go up 2 and left 1. And then from there, again, we'll go up 2, left 1. And now I'm out of space in that direction as well. So I've got all these points lining up. I can go ahead and connect them with a straight line, making sure to put arrows on either end, again, to communicate that the line continues in this same fashion forever. Okay, so here's a fourth example of a linear equation written in slope-intercept form where I see the y isolated, I see an x term and a constant term. And just looking at that format, I can identify the slope as well as the y-intercept. Now the slope is supposed to be the coefficient on x, which is the number in front of x. Now I don't actually see a number in front of x, I just see a negative sign. Keep in mind that the coefficient, when you don't see it, is a nice invisible 1. So my slope is actually -1. My y-intercept, again, is the point where my line will touch the y-axis. It always has an x value of 0, and then the y value is whatever the constant is, which in this case is -4. So when I go to graph from this information, I'll start with the y-intercept. It's the one point that I've got. So I'm going to go down 4 to get my first point. And then from there I use the slope to figure out how I go up or down or left or right from there to get my line. So again, we think of the slope as the rise over the run. We want to think of this as a fraction. One way to turn a whole number into a fraction is to just put it over 1. So I can think of -1 as -1 over +1. I can also think of it as +1 over -1. Both of those would result in a -1. And that gives me then a couple different ways to think in terms of my directions. Since this is rise over run, vertical over horizontal, I can think down 1, right 1. Or I could think up 1, left 1. So let's try, from our initial point, trying this first option here where we go down 1, right 1. So if I go down 1 and then to the right 1, I get another point, but these points are very close together. And if I tried to set up my straight edge, even just the smallest little change in these 2 points could make a big difference on the extreme end. So I want to get some extra points in here. I'm going to keep going down 1, right 1 from this point here, down 1, right 1 several times until I've got a bigger picture here. And I'm kind of working at an angle, so that might not be, that's not great, but we get the idea. From this initial point, again, I want to go a different direction. Let's try the up 1, left 1. So up 1, left 1 gives us a point here. Up 1, left 1 gives us another point. Up 1, left 1. Up 1, left 1. And I can just keep going until I run out of room. So just keep that pattern going until you run out of room. So we have a lot of points on this one. This one's a little bit overkill. But we had 2 different options. We had the down 1, right 1, or the up 1, left 1. And what we can now do is we can take these points and connect them with our straight edge, making sure again that we use arrows to communicate that the line that we just graphed does continue in both directions forever. So now what we have to look at is what happens when we're given an equation that's not written in slope-intercept form. How do we make it have slope-intercept form so that we can actually see this information right off the bat? So that's what we'll see in our next video.